A few practical things before we start. So this is a live event, so it means that there's a raise a hand button on your toolbar of GoToWebinar, so you can ask questions. And I think there's plenty of people today, so I cannot promise you that I will answer every single question I got today, but they will be recorded, and I then, if I don't have time, I answer my best to after the webinar. So that at least I can promise that I answer every single question after the webinar. And this is an introduction webinar, so you have to understand that we are not going very deep to details in this webinar. And this is the first of webinar series handling about the prefab. So we are gonna hosting more of these about the technical details what we start to discuss today. And this webinar is mostly handled by me and my colleague Casper. Casper, I think, is today in London, so he cannot participate, but I will be hosting the whole webinar today. And like I told you, this is the introduction. So if you think that I don't discuss about the details enough, that is like intentional. We go through all the possibilities we can do with our finite element software FEM-Design and post-processing software Prefab about the mostly wall elements and concrete frames. So concrete frames can be like a really complex thing, and the picture what you see in the background is a nonlinear model of concrete behavior, and it can be like really complex. If you look what's happening there's flaws which will take shear of the walls, then there's a cracking, there's a loss of stiffness, and a plasticity of the connections, and this is like hard thing to do with the complex model. And today we will look also the opportunities how we can do this the whole thing with the big models, with much easier. And today we look mostly methods which are based on the stiffness. So that will be like your classical finite element methods. So the stiffness of the finite elements will give you the distribution of the loads. And then we also look capacity-based distribution. So that will be like our plastic calculation. So the forces go where the capacity is, or like our crack section analysis or our plastic optimization tool, Prefab. So there's many ways to calculate how the internal forces goes in Prefab system. But most of them, they are based either stiffness or capacity, and then you can optimize the whole thing. And this is the content of today's presentation. So first we look at what kind of finite element model we have in FEM-Design. It's pretty unique, so that's why it's a good you know that if you have used some other finite element software. Then we look the modeling tools, how we can model those walls and elements in the FEM-Design. And then we look how you can model diaphragms, so it means floors and hollow cores and so on, lateral structures. Then we look the non-linearities we can do, and then how we can design those elements, and finally how we can plastic optimize the whole thing, like big building frames. So that will be the content today. So the first part is the finite element model. And if you do anything with FEM-Design, it's a bit like different finite element method than your usual finite element software. So the left side, we have a like classical finite element model where everything is connected, so they are like one single finite element mesh. But in FEM-Design, they are like separate finite element meshes, and they are connected by the connection element in the corners. What you can see with these text values. So text value will give you the behavioral model, how they are connected together. So nothing is like ultimate rigidly connected together, and you can see that how it compares to the classical finite element model, where we put the hinges directly inside of those finite elements. In FEM-Design, they are between those separate elements. And if you look at the picture on the right side, the elements go a bit like inside of each other when we squeeze them. So they are totally like separate elements. There's a total element separation between those walls. And the default stiffness in software, we have a default values for ultimate rigidity is 10 to the power of 7, and it will help you a lot when you're doing your finite element models. And if you compare that value to the stiffness of typical prefab wall, it's a 1 magnitude higher, so it's a 10 to the power of 6 or something like that for typical reinforced wall. So what happens when you put those edge connections. We always lose stiffness, and if you look the model on the left and model on the right has those connector elements between those, and the left one is when we have ultimate rigid connections. But in reality, it does not affect that much because the tension side is much more weaker in the connections of prefab. And anyways, there's typical frames have walls on each single side of the building, so only like if you have a really narrow walls or shaft, you have this thing that you lose a lot of stiffness. But that's how it works when you connect the element with the limited stiffness. And it helps you if you think our classical or like rigid finite element model on the left side, and our default model our default model will be on the left side, and the classical finite element model will be on the right side. If you look those peak values on the corners, those peak values will go away if you use like limited stiffness between the elements. So that is like we have developed this limited stiffness in the model. So nothing is, but of course you can also change the default value yourself, and the benefit is that you get more realistic design values because the concrete will soften after 50% or 40% of the capacity. And if you do contact analysis between wall elements, the limited stiffness will give you much better converging finite element model. And of course, you can adjust stiffness yourself, so they are found in the software settings in the connections. What is the ultimate value of the stiffness between the elements? Another benefit of our finite element method is that we can solve unstable models. So it can mean that we can, for instance, draw a single wall plane. We don't have to put any depth direction supports in the model. It just works. If you look this model, it just works just fine. We don't have to put any supports. And we have a stabilizing methods in the stiffness matrix. So it means that if we have a small deviation in the depth direction, it will be interpreted as 0 in the solver. And also we have a small spring values to stabilize. And also non-linear models work with these unstable models, as you can see. But this is pretty unique that you can do this. So all of these elements are in practice, they are unstable. And if you go into 3D, it's even worse because you can have a lot of elements. For instance, this shaft, we have these elements which is on the hinge support and hinge beam. So in reality, that wall will be unstable. But still, FEM-Design will calculate and give you the right load distribution. And here's the other example. It just solves the system and doesn't give you any issues about those unstable elements. So this is an unstable element. Then we have a usual default finite element. What we're using in the element structures are 9 element finite elements. And if you look the classical 4-node elements, you need a lot of like finite elements in the depth direction here in the beam, or especially if you have these walls and the prefab elements usually have really narrow strips. So it's important that you use those 9-node elements. So classical element, you can see that how many of those how dense the mesh have to be before you get like correct results. So here we need like 6, and here we need like, I don't know, 7 in depth direction. And if you go to the 9-node elements, even with 2 elements, it's almost like spot on the right solution. So that is a big benefit. And we also have another meshing methods here in the FEM-Design. So for instance, edge connections can be forced to always have a three elements inside of them. So we also take the connections into account of the finite element generation. So then we look those modeling tools, if some, or do you have any questions about those finite elements what we are using? Okay, no questions. But if there's any, I don't know, there I think I have noticed that there was hand button flashing there, but I answer after the webinar. There's a question. Let's see what it is. At least okay, it was just raise a hand. Okay, it was not a question. So we go to the modeling tools and look how we can model anything. So typical structure will look like something like this, and then we can look how we can make these walls with the FEM-Design. So they can be really complex. So we start with the plain wall. So plain wall is the magical button where you do like 90% of your element structure in FEM-Design. So it's on top bar in the structure tab, and on the plain wall, it's important that you define your connection presets because this will make your life easier. So this word what you define yourself, it's like, for instance, my word is RC wall type C, no anchoring. It has all the properties how the element is connected to its edges. So it will include a lot of properties, and we will look now what's inside there. So if you go to the settings of the wall, you see this picture on the right hand side. All of these words, like the behavior model of the connections on right, top, bottom, and left hand side, they are built into this preset what you save and use when you draw models. And if you modify a model, this will be automatically updated to the corners of the element. Then we have another thing what we talk about later. These are corner topologies, how corners are connected to surrounding elements, and we will look also what these will do. So you can access all of these properties with this big button in the wall tool. And those behavior models, these words can be defined here with the library. So for instance, here I have defined while loops connection. It has a K value. X is the longitude or shear spring value between the elements. Ky is the compression, and the tension side is 0. And we also have used the detach analysis here. I will explain later what that means. And we have also applied the plastic capacity of the connection in this field, so they can be put here. So the spring value in linear region and the plastic value of the connection, they are put here. And the detach analysis mean that if you have a compression, this red color here means that we have a compression between the elements. Also, if you look on the picture on the right hand side, you can see the shear forces. So shear forces will only affect those areas where there's a compression between elements, and that is the detach analysis in FEM-Design. If you do not do detach, it means that the shear forces will be affected in the whole connection. So how do we practice draw those walls? And first, I recommend you always like put on the types here, so you can put type names on the settings, and also color coding if it's a big structure, so you can really see what you have been defined on your finite element model. So the first technique is drawing those walls manually. And if you have defined those pre-settings, it's so easy, because if you draw anything, you get also those edge properties and corner topologies of your walls automatically when you draw them. So anything I draw, the connections will be already there. And if you want to place anything like holes, you can place them with the hole tool, and F12 you can fit the coordinates. For instance, here I move my mouse back to the starting point, and now I can input the size of the hole. So 1 meter times 2 meters is the size of that hole. And of course, holes can be located anywhere in the element. So and you can copy holes and move those holes if you want. And modifying the model is pretty easy. It's a right click and move, copy, stretch, rotate. Unique feature what we have is we have this modified region command. So it means we can split regions. For instance, here if we want to divide the element, and you see what's happening with the connections. Connections will be generated automatically when you split the element. So you don't have to know exactly what is the element division. You can modify it afterwards, or you can connect two elements together. So it can go both ways. You can divide them or connect them together, or you can even add like new areas to the existing walls. So it's really easy to modify the plates or the walls. So you don't have to like be blocking your design in the get-go. You can modify it later. Second option is the importing of the IFC model to the FEM-Design, and it goes usually my process goes in 4 steps. First, we remove small details, so it can be holes and like those details on the edges. Then we align elements to the plane, so everything will be flat. There's always like floating point or decimal errors in IFC files. And finally, we stretch corner points of the elements to the grid. And finally, tool is what I usually use is adjust of analytical model. So if you have jagged edges, you can remove those from the edges. And in practice, it will look something like this. So we have imported IFC file. So it has intentionally made big errors there, but usually those deviations are much smaller, but you get the idea. And we have defined accesses here. So stories and accesses, and these will be used as your master objects. Then we just select correct model. And the first operation here is alignment, or sorry, fixing of the small areas. So all the small details, which doesn't mean structurally anything, will be removed like those. details. Now it's more simpler. Second option or method is to align everything to the plane. So that's what we are doing now. And once we start the operation, everything will be now located on those axis planes. So everything is flat now. And the final fixing operation is stretching those corner points of the elements to those axes what we have been defined previously. If something is not get fixed, usually it's a causing of tolerance. If you have small details on element corners or element edges, it doesn't fix it off if you put too high tolerance. And the final tool is adjusting of the analytical model. If you have a jagged edges like we have here on the right, here, or here in the corner of the shaft, so they will go now. So first we put it on between the axes, and finally we can make the finite element mesh to prove that everything is connected. So that's basically the IFC import process. But we will look this later in the upcoming webinar, so I don't want to go too deeply into this. But then you continue normally just by applying the connections between the elements. And then we have also option to using AutoCAD files, drawings of AutoCAD. But that's simple. We just import the lines from AutoCAD file, and then we select those lines. So we can make walls, columns, or beams with the lines, and we just select the anchoring or the edge connection type, and those will be imported automatically. Downside of the AutoCAD file is, of course, we cannot import openings to the models. And here is the example how you can use AutoCAD points to define columns in your prefab frames. So openings have to be added afterwards, as done here. So because AutoCAD file is usually it's a 2D file, so you have to add openings yourself. But that is not a big deal in FEM-Design. I always advise if you are a beginner with FEM-Design that you don't use AutoCAD files because they might include small errors like decimal inaccuracies and so on. So one recommendation is that you never snap to the AutoCAD file, or you use those fixing tools I showed you before with the IFC, so you can fix your. But there's always some geometric deviations in AutoCAD files, and that can cause issues with the finite element models. But learn those fixing tools, and then it will be like really easy to also. You can just draw it like almost like not perfectly, and then you fix it to make it perfect. Any more questions now? Okay, we can continue. Next, we discuss about this unique feature about how we handle element corners in finite element models. And it's called separate endpoint in FEM-Design. And there's three main cases for separate endpoints. So first case is always when you have very different behavior models in your crossing connections. Second one, if you have want to have total balance between the story force and wall connection forces. And this is really typical if you have used any other finite element software. This is really typical problem. And if you want to have totally moment separated multi-story columns, I can show you examples. And some use it also for beam connections to the wall edges, so the beam will be connected only for the bottom wall, not the top wall. But let's look how it works, the main case. So here we have a finite element model with the connections, vertical and horizontal connections. And if you zoom in on the right-hand side picture here, we can see that the horizontal we have defined hinge, and on the vertical connection we have defined on the other side of the connection that it's sliding or like it can move. And this is the point of contradiction. We have like a lot of stiffness in vertical direction in the horizontal connection, but the vertical connection can move. And if you calculate the finite element model, this will happen. If you look those corners, there's something like wonky going on. And there's few clients who use it as their benefit, but I always advise that do not do that, because the problem if you want to model with this technique something, they say that okay, there's a welded connections in the corner, so there's a flaw in between the walls, and that will take the shear, and this will model the flaw. But the problem with this technique is that it's very sensitive to the mesh size. So on the right hand side, you see what happens with without endpoint separation. If you have a 50 millimeter mesh, in the mid you have a 300 millimeter mesh, and on the left hand side you have 600 millimeter mesh. So if there's this corner topology problem, it's really sensitive to the finite element size. So I recommend that you solve it, and you solve it by applying those separate endpoints, and you have a button in the wall dialog to do that. So first you select walls, then you select connections, And finally, you select that which of those endpoints will be separated. So I will say that, okay, they are separated. And there's a small button or this dot symbol in the corner of the edge connection, which will tell you that, okay, now the corner or the endpoint of that wall will be separated for the finite element model. And now if we calculate the finite element model, here is the original, and here is with the separate endpoint, and the problem has gone away. So now it's a totally separated and perfect finite element model. There's no any hidden stiffness in the finite element model. So that is the first use case for separate endpoint. You have a contradiction of the stiffnesses in the corner, and that will solve it. Let's look at the second use case of separate endpoints. So on the left hand side, you don't have any separate endpoints, and if you sum up these to shear forces of the walls, they do not add up to the total shear force of the wall. And in FEM-Design, because you're using edge connection, the difference is not big. But if you're using some other finite element software where there's no like a separate topology between the walls, it can be big because the edge node will belong to both walls. So there's always contradiction, and which wall should have the corner point forces. And in FEM-Design, you don't have that problem. And if you use separate endpoints, you are in the perfect balance of external loads. So the story shear forces matches to the shear of the wall connections. So your model will be perfect if you do it like this. And the third use case is this, that if you have a continuous column over through the one floor of precast system, and if you zoom in, we have applied the endpoint behavior in the precast elements of the column corner, and now column will be totally separated from the floor, so there's no any bending transfer between the floor and the column and the beam. Everything will be separated. And also the shear forces are not going through the column, so everything goes first to the beam and through the beam to the column, so it's like a perfect topology of prefab system. So we can see that the bending moment diagram of the column is continuous. There's no any jumps, so it means that it's not connected to anyhow to the floor. How we model anchoring in FEM-Design. So if you want to do nonlinear models, the anchoring can be option. And we are using a command called truss member, and truss is only connected to the endpoints to the finite element models. We can even introduce the limit force for those trusses, and they are just simply drawn over the walls. And they are not connected to the edge connection at all, so they are only connected to the element itself and on the endpoints, and anything between are not connected. And there's actually two ways to draw those trusses. First one is like this, that I draw them with the elongation length, or the other option is that I draw one long truss like this one. But the first one is correct if you want to do nonlinear analysis, because you need a correct elongation length in your tensile members. So it will be like if it's like a wall shoes, it's probably like a distance of your threaded rod inside of the connection, plus some stiffness of your flanges. And if it's like a rebar, take into account like the 15 times the diameter inside of the wall, and that is probably pretty close to the elongation length and right stiffness or tensile stiffness. If you put those anchors and calculate your finite element model, it will look like this, but it requires contact analysis to work, of course, otherwise the element connections itself will take the tension. But now the anchor is in the tension component. So the deformation of the prefab system is typically like this, that if you have a lot of lateral load and not lot of compression, the most of the deformation will happen on tension side. So the compression side deformation is pretty small. It's mostly happening in the tensile side. And if you have a windows, the shear deformations are really significant in the prefab system. So how do we model those flaws in the finite elements, and what are tools in the FEM-Design? Basically, there are many. We have like 4 main categories of lateral systems or diaphragms. First one is continuous shell, and that's like obvious. It's a shell model with the right stiffness or linear stiffness, uncracked stiffness. So it's a normal shell model, and it can be linear or non-linear. And always what it produces that the floors are semi-rigid. The second is a bit like unique. It's a non-continuous shell models, what you already have seen on previous pictures. So it means that every single hollow core is a separate finite element model, and it's connected with edge connections to the others. And even that's semi-rigid. rigid floor system. Third one is ultimate rigidity. So it means that we use a tool called Diaphragm. Diaphragm will make the wall like ultimate rigid, so there's no any shear deformation going on in the floor. And that is basically what most of the prefab systems will work. So most of our buildings, what we are looking outside, it's like the buildings are pretty like square or rectangular, and they are not that narrow. But in cases if you have like openings, atriums, you have like narrow buildings, maybe then you can consider semi-rigid or no rigidity at all, because then that is more correct way to calculate the prefab. But most of the buildings, only the deformation of the wall will matter in the overall system. So the diaphragm will make your finite element models much simpler if you want to remove the flaws from your model and only take into account the stiffness of the walls. And the last one is called no rigidity. It means that we don't model the walls at all, and because we can solve unstable models, we can separate all of the walls like totally. So even in the corners, we can separate all the interactions. So it matches the old-fashioned hand calculation, where only the stiffness of the wall will tell you how much force it will take if you take into account its location to the shear center of the building. There's always good sides and bad sides of all of these models. Like for those which have like limited stiffness, it's good for SLS because all the stiffness is in the model and you get realistic deformations. And the downside, if you have those shell models in your model, is that there's always like vertical shear transfer, what we look next between those walls. And this no rigidity model is also pretty handy if you want to be on the safe side and the building is not that high, so you are in a mid-rise region. So that is like really sweet model for there. But all of these have like good properties and bad properties, and it's up to you what project you are doing and what kind of theory you want to do. So the question is, should you apply the diaphragms to your model? So for this case, if you look like this model, the walls are sliding with each other, and you can see that also some forces are flowing through the wall, like in this area and this area. And this is really difficult to isolate in finite element models, how much this shear is now transmitting through the floor, and it's very hard to quantify and take out of the model. So that is like the downside if you want to add like floor plates. And also you have to now design this floor plate for secondary bending because this will stabilize your building now. So it might make a lot of sense to remove those flaws. But in reality, if you have a thick cast inside floor plate, it will totally take the shear of the wall vertical connections. That's what happens in reality. If you have some other case like you might have like hollow core, so now the only component between the walls is the growth or the filling concrete, and that is not as strong and might be easier to put on your behavioral model of your wall connections if you have like this case. In this case, I have used the shell model where I have reduced the stiffness on the secondary direction, but still you cannot quantify how much is flowing through the floor. So they are always like problematic to use the shell models. Third option is to use those diaphragms. So they are drawn using the diaphragm tool, and it's really easy. You just give it a name and then you draw it, and now everything what is inside of this diaphragm will be ultimate rigid for shear. And in the calculation settings, you just put it in the rigid membrane. You never use the last one because that is for raft foundations and very thick plates like rigid bodies. So this mid one is the right one. And if you have succeeded with the calculation, this is roughly what it looks like. By the way, vertical loads have to be dealt with somehow if you don't have any shell models in your building, and we have a tool called Cover, and that's what this video is showing you. So Cover is a tool what will distribute the vertical loads, and that will simulate the load bearing of the hollow cores, and it doesn't have any stiffness, so it can be combined with the diaphragm really well. So it's just a cover which will tell you that you can define which are the load bearing members. So you always select walls underneath the cover to take the load, and then you can select the loading method or load transfer method and what are the load bearing members, and then you can use surface loads in your buildings. And if you have succeeded with your model, it should look like this, because now they can slide. So the diaphragm will bind those walls together in the horizontal direction. And if you have any bigger model, they will look something like this, that they are bind together, so you don't need any floors. But of course, you can add also shell models in here, but then those shell models will become shear rigid, so they don't have any shear deformation anymore if they are inside of the diaphragm. And you can also use it if you have some regions, like we have a square building, so probably there's no any shear deformation going on in this part of the building. And same here, but in between we might have some semi-rigid regions. So we can only exclude or include certain areas to the rigid diaphragm. So we can use semi-rigid theory in between of those buildings to really like save those finite elements for the important use, not to use them for the walls. So there's a flexibility in the middle. You can even use no rigidity at all in this area if it's like really only few hollow cores, or you don't want to take the growth or the edge pass into account. And finally, we have this method which doesn't have any stiffness, so the floors are not modeled and the floors are not in the model at all. So then we need some method to put the wind load on those walls, and we have a tool called core wall or shear wall wind load. And now we can decide that what is the criterion how we distribute those loads. So we have an exponent. An exponent will tell you that do we want to use the bending stiffness, so that will be exponent 3, or shear stiffness. So if the exponent is 1, it means that only the length of the wall will tell you how much force it will take. So if the wall length is double, it will take the double of the load. So this tool will calculate the shear center of those core walls, and it will distribute those wind loads to the walls. So we don't need any walls or floors in the model, and we don't need that rigidity because we distribute those loads with the other methods. And Eurocode Annex E is pretty much the same method. It only uses bending stiffness, not the shear stiffness. But we will go with this method or show you more information in the upcoming webinars. Then I wanted to give you a few examples of nonlinear stuff what we can put our finite element models. And the example structure is this: it's a shaft with the elements, and we have also modeled those anchors in the model. If we zoom in, we can see that on those vertical connections we have used behavioral models. So there's a stiffness and there's a capacity, and that's inside of that wire loop 600 no contact word. We haven't put contact analysis in vertical connections because of the numerical stability, and I will explain these principles in the upcoming webinars. And on the horizontal connections, we have just put the double, so it means that there's a contact analysis only on that connection. And this is our behavioral model, so we have put that the capacity of the wire loops is 70, so they are fed in this field. So all the vertical connections can only take 70 kilonewtons per meter, and the horizontal connection cannot take tension. And of course, we have to use the endpoint separation, as you already know. We also have really classical problem here that we have a lot of load on the one side of the structure, but not on the other. So the vertical connections will have a lot of stress in this case. And same happens if you're using hollow cores. Hollow cores will distribute the loads only in one way. And if you notice, there's a few loads are blue and few ones are red. The blue ones means that they are assigned to certain structure. So we have to assign this load to make it go the wall under the load, not on the top. So this load will be placed on top of this wall, not on the underside of the top wall. So to assign, we'll fix that one. First, we run linear calculation. So we can set non-linearities by the combination. So this is the combination settings. So we just put the calculation. And the calculation times is pretty easy. It's like or cheap. It's 2 seconds per load combination, this size of the model. The next one we checked is the NLE. So now the contact is done between the elements. So you can see what's happening here. The contact will be opening between the walls on the horizontal connection. And the calculation time or the calculation penalty is a bit higher. It's at 10 seconds. And third is the plasticity of those connections. And now the calculation penalty is really a lot. So you can see how much it grows. It's 130 seconds. So it's if you're using plasticity or check the PL tab for combination, it will use a lot of calculation power, and it cannot be done to really big. But these are like shaft models. They are really easy. about 2 minutes per load combination, and you are done. But big models, maybe if you apply only part of the model, it's really easy to do. But like 10-story or 20-story building, it's almost impossible to do. So this is what's happening. So now we can prove that we have a balance with the external loads, with the plastic capacity of the connections. We have also really good features in FEM-Design to look the edge connection forces, what I'll demonstrate here. So we can change between different distributions. So we can post-process those element connection forces. We can use triangular distribution, or we can use plastic distribution or raw data from the finite elements, and we can see that now the contact analysis have been removed. So this is the result from the contact combination, the mid one, and we can see that the vertical connection forces are like 190 here, 101 here, and 72 here, 147. So our capacity was 70, so we are a lot over the capacity in the vertical connections. But what will happen if we go over the capacity? The plasticity will distribute the loads in some other way. So we are using plastic ductility to distribute the loads. And on the right hand side, what happens if you turn on the plasticity? The forces do not go over the limit. So then we can prove that we have balance and what are the deformations, what follows, and how much slip we have per connection. So we can also check that how much plasticity is needed. And software will tell you that which of those connections will be plastic and which are still in elastic region. So this is an example of nonlinear analysis. And the final example of nonlinearity is the cracking of concrete. So for instance, this model, we have tensile stresses over 25 and compression stresses of over 25. So that's a lot. So our model will look like something like this in reality. So there's a lot of cracking in this transfer beam over the door. So how we can do that one? And the problem with the linear model is that now this part will take way too much forces in our finite element model. So even the global forces are not correct in this instance. So how the nonlinear is done is first we apply the rebars to the shell elements. So we have a rebar tool where we define the rebars plus the anchorage of the rebars. We put meshes and single bars. Then we turn on the nonlinear models, and it can be only turned on for certain walls. So you don't have to put nonlinearity to the whole model, or you can just put it on one model, or even divide the element and put it just one small region of one element to really make it fast. And here we have a difference between the left-hand side, we have a nonlinear model, and on the right-hand side, we have a linear model, and the left-hand side has been cracked. And here's the compression stresses of concrete. Tensile stresses will be gone in the concrete because it will crack. And then we get the plastic status where the cracking has happened, what is the cracking direction, and where are the elastic regions. And red color means that where the compression is over 40% of the capacity. And finally, we get the rebar stresses, and we also get the strains out of the system, so we can check the ductility of the system. But of course, it's the calculation penalty is really high. For these two walls, it takes like 2 minutes to calculate with the cracked model. So calculation penalty is high. Instead of we can use stiffness factors. So each of those elements in a FEM-Design or element subregion can have a stiffness factors. And it's a pretty basic concept. We are using the second modulus of elasticity instead of E modulus of concrete to simulate the effect. So how to do it in FEM-Design is this. First of all, I want to modify region. I want to isolate. So I divide the element and only put the cracking factors or stiffness factors to parts where there's really something cracking going on. So I go to the stiffness factors, and I can even set them by limit states. For we can assume that in SLS or service limit state there's a minor cracking, and ULS there's a lot of cracking. And I can feed to these separate finite element components those cracking factors. And of course, if the other wall was also cracked, I can also apply the cracking factors there. So now I can use linear model and roughly get the right results out of the system. And if this is the initial state, the linear model without cracking factors, and if we apply cracking factors, we can pretty closely match the nonlinear model without the calculation penalty. But it requires a lot of expertise. And I always recommend how you do it. You do it by envelope. So first you estimate what is the upper bound of cracking and lower bound of cracking, and then you calculate those two states of your model, and then all of your internal forces have to be inside this envelope. So because there's a lot of uncertainty, the envelope is way to go. Then we quickly look what we can do design-wise with the FEM-Design if we have elements. So first of all, we can introduce buckling. So we can put buckling direction if the compression is not perfectly like vertical. We can put Euler factors, so how much there will be slenderness, and we can take the supporting effect of the surrounding walls into account. And then we can check that where the utilization is too high. And utilization means detailing rules, cracking, crack width. It can mean capacity, buckling, and we also get really nice report out of those shells. So it will include the buckling as well, and cracking and minimum reinforcement, maximum rebars checks, and so on. We can also design element parts like strips or transfer beams as a beam. So we can change any element part to the beam, and these beam parts we can get report. Like here we have a fire resistance of the concrete of the transfer beam over the wall, and we can set the fire exposure on different size and get the capacity. So the shell models will be integrated in the beam, and the beam we get fine report. Okay. Final part I want to discuss today is the plastic optimization, unless you don't have any questions. Okay, there's no. We have questions. I was just like lazy. I didn't look. Let's see if I can use this tool. Question is, can you see how wide the cracks are in the plastic model? You can see the strains in rebar layer, and you can calculate it afterwards with the strain. But to get crack width, you need some kind of theory. And this is a smeared rebar model, so we don't simulate each single crack, but we simulate the effect of cracking. Correct strains will follow, and with the strain, you have to take some theory book or the dimensioning standard to calculate the crack widths. But no, the model does not directly give you the crack widths. It just gives you a strain, but maybe we develop it in the future if we implement some formulas there, because the crack width will be dependent on how you place your rebars and what kind of theory you calculate those cracks. In FEM-Design, if tension occurs in the foundation, how can we perform nonlinear analysis similar to other software like Robot? For example, in Robot we usually set the whole model to nonlinear analysis except the gravity loads. I don't actually understand how this question. I will promise you answer after the webinar, so we can probably have a way to do that. There's a question also. No, it was exactly the same. So if I don't find the answer, I will return to you after the webinar. So for the plastic optimization, we are using software called Prefab, and it does like one thing really well. First of all, we can have FEM-Design model which can be linear and non-linear. Then we feed it to Prefab. It will give you new load bearing, because now it will take or move the capacities around. It means that if we have, for instance, the shear capacity is exceeded on one point, it will move it to next, and totally when the total shear line or one wall line shear capacity is exceeded the total capacity, then the stability is lost. But we will look with the examples, and what it spit out is the total new load takedown with the optimization. It also give you element report. So if you want to give some paper to the element designer, this will give you the loading to the certain element and the grade of element size of the opening. So you can design actually the whole element and calculate the whole element with this data. And third thing it can do, it can generate the totally new finite element models out of the original model. So we, for instance, first we have a linear model, then we do plastic optimization or this redistribution, and then we generate the model of the shaft or model of the wall with the new optimized forces. That model can be linear or non-linear. And this is an example what happens with the plastic optimization. For instance, the tension anchoring, we see that there's a tensile forces, but after the optimization, we can conclude that we don't need those tensile anchoring because the stability can be guaranteed without tensile anchoring. That is like one way to optimize the structure. Other way is that we have exceeded the shear capacity here, so we move it to the other locations in the structure. And the prefab is mostly based on following assumptions. So elements are mostly monolithic, so the deformation happens in connections. And we also have like an option, or we have what it does automatically. If there's a window or door, it automatically removes the compression out under those windows if it's like minimal. Then we assume that the plasticity of the connections and concrete compression zones will distribute the loads to the places where the extra capacity is still remaining in the structure. And we also always assume that we have a plastic ductility to distribute those loads. And wall diaphragms, they are not verified at all, so they can do whatever. But it's better to look at that in practice. So first of all, we have a FEM-Design model here. So it's a non-linear model, but it can be linear model as well. And then we get our deformation. So we get uplifts and tensile forces. And the prefab can be started with this button on top right-hand side of the FEM-Design. And what will happen? It will start the prefab. And if the model is not showing here, you can click this button to update your model. So it will read the FEM-Design model back. If you have multiple models open, it will ask which one would you want to use for plastic optimization. Now it will calculate, and it will also give me right away the highest utilization in the whole wall system. So now the utilization of our stability combination is 110%. We can see where the problem is. It's this wall here. What we can now do, we can look the report, what the report is look like with the FEM-Design internal forces. So now it will do just reporting. So it means that we are using the original load takedown from the finite element model. We don't do any optimization now. I will do the optimization on the next step. It takes some time, but I intentionally made a smaller model so it's able to handle in this webinar. So first of all, there's instructions how to use this report of the takedown, like examples. Then it will give me my floor plans. It's not that impressive when you have just one wall. But then we also have elevations, and then we have an overview, so we can see where the maximum utilization. And this is an interactive PDF, so everything can be clicked here to get more information of elements. Here is the loads of the element, and this is probably the most interesting part of the report. So we can see how much there's a tensile forces in the system. And if you give this PDF file to anyone, he can just click those arrows and regions to get more information. For instance, what is the length of the shear zone or compression zone, and what are the forces flowing through. And then you can also see the utilization of wall and connections. If you click here, you get all the inspection formulas for the wall. What is the problematic factor? Now it's a shear capacity is exceeded in the connection, and also sliding capacity is exceeded. And if you click there, it will show you in the 3D model where the wall is located. It's located here. And for the element designer, it will make one report per wall. So you can now take this one paper and give it to element designer, and he can design the wall, because you have dimensions, you have a mass, you have a strength class of concrete, you have tension anchorage, location of those, and also loading, like how much is the compression, where the compression is located in the element. So you can design the foundations. And now the fun part, if the utilization was over the limit, we can now optimize it again. So we go to the plastic, and now we do not select based on the FEM-Design, but we select the new optimized plastic redistribution. So now we'll move those shear forces where the capacity is, and we can right away say that the right utilization is 62, so it will be okay. And now we can print the new report where there's a correct utilization, but I don't do it. That takes too long. And now you can see that this one wall is green. Then we can export. So now we can generate those extra finite element models based on new load takedown. So there's an export button, and here's the things we can export. The reaction means that if we have a foundation model, we can export the reactions to the foundation model. with new plastic distributions. So we have moved those compression locations based on concrete capacity and the optimal overturning of walls. Wall elements, this is really handy if you want to do wall element design with the FEM-Design. Or third option is that we can select any component in the 3D model of prefab. So for instance, we can select these one wall line, or we can select one shaft, and then we can export this to the FEM-Design model. So we can make new finite element model here. But if you want to do the wall model, it will look something like this. So I will open this one. So it will like export your whole model. So now all the essential information is new finite element model. Also the loading, that plastic loading, what we have been used after the optimization have been imported here. So now you can really use non-linear tracked model to calculate this one wall or all of these walls. If you are not that interested or want to just design one wall, you just simply delete all the others in this model, and now you just have one stable model which will have external loads. But if you have like want to use crack section analysis, I would recommend to place these upward pushing forces with the supports, because then it will be stable also in non-linear models. But if you want to use linear calculation, it's just ready. You just press analysis and calculate, and it will calculate the model where these forces will perfectly balance each other out. And you can design the rebar and calculate wooden armor and so on. But that basically is how it goes. So do you have any questions about FEM-Design? If not, I hope you have learned something new. And like I told you, this is just an introduction. If you want to go deep into details, we have a lot of upcoming webinars about the prefab with me and Casper. So with the non-linear model importing of the IFC, modeling tips, techniques, how to get non-linear models to work, and so on. And I hope you had fun today, and see you at the next webinar.